Okay, today we're diving into the invisible systems that pretty much run our entire physical world. From the lights in our homes to the water in our taps. And we're going to explore the hidden dangers that pop up when we try to make all of these things smart.
So let's just start with a huge question. What is actually stopping a hacker from just turning off the power grid? Seriously, this isn't some plot from a movie, it's a very real problem that a lot of smart people are trying to solve right now.
The answer to that question really starts with understanding these invisible brains that are operating all around us. We're talking about the systems making decisions behind the scenes that have very, very real physical consequences.
And this slide right here gives us a great little blueprint for how these brains work. So it all starts with sensors that read information from the physical world. Think of a thermostat reading the temperature in a room. That data then goes to controllers, which is the computing part, and they make a decision. And then finally, actuators take an action, like kicking on the furnace. It's this constant feedback loop between the cyber world and the physical world.
Now, the official term for this whole setup is a cyber-physical system, or CPS. It's really all right there in the name. It's this deep, deep integration of computing, the cyber bit, with the physical things they control. This is the key piece of technology we've got to wrap our heads around.
And trust me, these systems are absolutely everywhere. The electric grid, the pipes that bring us water, our transportation networks, and more. And more, things like self-driving cars and even critical medical devices. The stakes for keeping these things safe and working correctly are, well, incredibly high.
So, to protect these critical systems, we've basically relied on two different kinds of experts. It helps to think of them as two separate teams of guardians, and each one has a very, very specific job. And this really shows you the divide. So on one side, you have Team Cyber. These are information security folks. Their job is to build digital walls, stop people from breaking in, and protect the data. They're basically looking for hackers trying to get in from the outside. Then, on the other side, you have Team Control. These are control theory engineers. Their world is all about physics and reliability. They design systems to be stable, to handle random things like equipment failures or weird signal noise. Their whole focus is just keeping the machine itself running smoothly.
But here's the problem. A really clever attacker doesn't go where the Guardians are looking. They operate in the blind spot, right in that gap that exists between these two different fields.
And this brings us to a really specific kind of threat, the deception attack. See, this isn't about kicking down the front door. It's more like whispering lies into the system's ear. The whole goal is to feed the controller bad data that it actually thinks is true, which then causes it to take the wrong and potentially disastrous action.
This diagram from the paper we're looking at shows you exactly where this can happen. An attacker doesn't need to take down the entire network. Nope, they can just compromise a single sensor and tweak its readings. That's attack A1. Or they could intercept and change the commands going from the controller to the actuator. That's attack A3. It's like a surgical strike on the system's whole perception of reality. So let's just walk through it. First, an attacker gets control of just one sensor. Second, that sensor starts sending data that's false, but it looks believable. Maybe it's a pressure reading that's just a little bit high, but not so high that it sets off some blaring alarm. Third, the controller sees this plausible data and does what it's programmed to do. Maybe it opens a valve to relieve what it thinks is high pressure. And finally, that wrong action pushes the real physical system into a dangerous state.
And here is the absolute crucial point. This kind of attack slips right past both of our guardians. Team Cyber doesn't see an intruder because the bad data is coming from what looks like a trusted sensor. And at the same time, Team Control just sees what looks like a minor sensor glitch or some system noise, which is exactly the kind of thing their algorithms are built to smooth over and ignore. Neither side has any idea it's a deliberate attack.
So this dangerous gap means we can't just rely on our old methods anymore. We have to forge a completely new kind of shield, one that combines the expertise of both of our guardians into a single, unified defense.
And that brings us to the solution that's proposed in the research, defining what's called the secure control problem. The goal isn't just to prevent attacks or to handle random failures anymore. The new goal is to design systems that can survive, that can maintain their critical functions even while they are actively being attacked.
Now this new shield needs a totally new blueprint. It means security experts have to start thinking like control engineers, and control engineers have to start thinking like security experts. Our defenses can't just be digital walls anymore. They have to understand the actual physics of the system they're protecting. It's really about building proactive defenses that can anticipate what an attacker might try to do to mess with the physical world, not just the data.
Okay, so let's bring it all back home. Why does this super technical discussion about control theory and information security actually matter to, well, all of us?
It matters because that line between our digital and physical world has basically vanished.
Our safety, our way of life, it all depends on these cyber-physical systems. And securing them isn't just a software problem, and it's not just an engineering problem. It's this new, hybrid challenge that requires us to bridge the gap between those two worlds.
And that really leaves us with a final and pretty important question to think about. As we keep building a world that's smarter, more connected, and more automated, how do we make sure we have the wisdom and the foresight to ensure that it also stays safe?